All right, for this particular problem, we're going to do a half-life and we're going to use carbon-14. And I've just Googled, the half-life of carbon-14 just to show you 5,730 years. Okay, so let's go on to the problem. So this is the problem. It says the original amount of carbon-14 in a branch of a tree was 6.53 grams. The branch broke off and was buried. An archaeologist digs up the branch and measures the current amount of carbon-14 in that branch to be 5.79 grams. How long ago did that branch fall from the tree? And of course, we're given the half-life of carbon-14. All right, so of course we're going to use our. So what's important about this one is, it's definitely not going to be 5,730 years, right? That it's going to be far less than one half-life. I mean, you don't know that yet, but you're going to see that in just a second. Okay, so we have the equation. All right, so let's write this out. So n is, let me make this a little bit bigger. Hold on. All right, so you can see that a little bit better. So n is the amount remaining. N sub 0 is the original amount, right there. There's the original amount. This is the amount remaining. T is the that's the amount of time. All right, so let's figure out how we can do this particular problem. All right, so all I've done here is I've taken this n sub 0, the starting amount, and divided both sides by that. All right, you don't need to know how to do this. Okay, I'm actually going to give you the formula for this, but I just want to show you where this comes from. All right, so then what you do, so once you have this equation right here, what you do is you take what's called the natural log, all right, of both sides, the natural logarithm of both sides. And so when you do that, then and on your calculator, that's the ln button. All right, I'll show you that in just a second. All right, so what we're going to do is we're going to take the natural log, and so it looks like this. It's the ln. You take the ln, natural log of both sides. All right, so we're taking the natural log of this entire thing, and this it actually turns. So what happens is the thing that's that the exponent comes outside, right, and so it becomes this becomes the ln of n over n sub 0. This is actually, it's not really that hard once you see this, and then it's t over t1 half, right? So that's how you get that out of there, and then it just becomes the natural logarithm of 1/2, right, like that. All right, so that's and then you solve this equation for t, right? So you just multiply the t1 half on both sides, and you divide by the natural logarithm of 2. Right, because this is the natural logarithm. Another way of looking at it, it's the natural logarithm of 1 divided by the natural logarithm of 2. It's just the way logs work, and then this is really what you want to write. Okay, so all right, so all I did up to this point is not anything you would ever have to do. Really, what I was trying to do is get to this equation right here. Okay, so I'm just trying to show you how that equation comes about. I would never require anybody to actually do the steps to do this. All right, but this is the formula that is used to determine how much time has gone by. Right, if you know the original amount, that's n sub 0, the amount of the the carbon-14. Well, this actually works for more than carbon-14, any radioactive substance, if you know the half-life of the radioactive substance. So n sub 0 is the original amount, n is the amount, that is remaining after a certain amount of time, t, right? That's what we're looking for. This down here is just a constant negative, the natural logarithm of 2. So that's just a constant. And the reason I didn't write it as, 0.63, negative 0.63 is because, it would just be an approximation. All right. So, this is the exact value. All right. So these are the numbers that go in for our particular problem. We had carbon 14. We started out with 6.53 grams, over a certain amount of time, t, right, which is what we're looking for. 5.79 grams of carbon 14 remains, right? And we know the half-life of carbon 14. It's 5,730 years. All right, so let's write all these numbers into this equation, and then we'll use our calculator to figure out what t is. All right, so I'll show you how to do that right now. All right, so from our original problem, this is the setup. Okay, so I'm now I put all the numbers in. I'm going to show you how to do this calculation. I mean, this, it looks complicated, but if you just do the right steps, and make sure you have a natural log button in your calculator, and the other thing is make sure you do what's in parentheses first. All right, so here, so this is it. This is what we're going to do, and the answer will come out. Notice, the number of grams cancel. I didn't really show that here, but this is grams divided by grams. The 2 is just a pure number. And so the answer comes out in years, right? Because that's what the half-life is in. All right. So let's go ahead and do this problem. I got to get a scientific calculator so you guys can see that. All right. So there's one. There's the natural logarithm button right there. All right. So for example, if I want to say, -1, right? So -1, -1. So that's right here. I'm doing the denominator right now just for the heck of it. And so what you do is you're going to say times, and see, I got to put the 2 in first, 2 natural log. All right. So the natural log of 2 is 0.6. It's a decimal. It gets really, it goes on forever. All right. But, you can just approximate it by 0.639, 0.693. All right. Anyhow, when you multiply that times -1, it becomes negative, right? I mean, that's nothing profound there. All right. I'm going to store that because I'm going to divide by that in just a second. Okay. So I'm just going to hit this M plus, so that adds to memory. All right. So look, watch, if I clear this and I hit MR, which is recall, see, there's my number right there. All right. So that's what is in the denominator. The other thing is, so again, you got to do what's in parentheses first. So, take this 5.79 and divide it by 6.53. Okay. So 5.79 divided by 6.53. All right. So then you hit equals. All right. So that's what's in the parentheses. And then you just hit the natural log button. And so that's the natural log of this fraction. And then remember, we got to divide that by the negative times the natural log of 2, which I've already done. Remember, I've stored that. All right. So divided by, and I'm going to hit recall. Remember, that's the number. And see, now it becomes positive. All right. And so this is the amount of time that's gone by. It's going to be the half-life times this small fraction. All right. So it's just a small fraction of the half-life. So, basically you can kind of think of it as 17%, 17.4% roughly of the half-life. All right. So anyhow, you just say times the half-life, which is 5,730. And bang, look, so that's the amount of time that's gone by. The amount of time is 900 and so here we're going to round it to one place past the decimal to make our lives simple. So this is 900. Sorry about that. Here, let me write that. So it's 994. 94. Where'd my calculator go? 994. Whoops. 994. And see how it's 0.26, so it's going to be 994.3 years. So I'm going to put a little decimal 3. It's supposed to be a 3. That doesn't look like much of a 3. 0.3 years. All right, so that's how you figure out how much time has gone by. Here, let me rewrite it just to make it look a little clearer. So it's 994.3 years. Remember, if you were doing this kind of problem in Blackboard, it would ask you how many years, and so you would just put the number, right? And it would say something like, rounded to one place past the decimal. All right, so that's exactly how you do this problem. That's essentially how it works. All right, so let's do another problem exactly like this, but now we're going to use iodine-131, which has a half-life of 8 days. Let's say you were injected with, so somebody was injected with 7.2 milligrams of iodine-131, which is radioactive. When there's only 0.05 milligrams left, how much time has gone by? So let's set that up exactly like we just set up the other one, right? So we're going to put the numbers into here and solve. All right, so this is how we're doing it. It's the half-life 8 days, the natural log of the amount that remains. This is the amount that you started with, and it's always divided by negative the natural log of 2. All right, so let's get our calculator and we'll try to do this. All right, so I'm going to do the denominator first. So for this particular, other calculators, by the way, you usually have to hit ln first, and then it'll have parentheses. But for this particular one that's on the computer, you have to hit 2, and then the natural log. See, there's the natural log of 2, and then just hit the negative sign to make it negative. All right. So I'm gonna store that, whatever it is. Okay. So here I can clear it. See, I can recall it. All right. So, whoops, that did not store correctly. Hold on, let me redo it. All right. So now I had something stored in there, so that's why there was a problem. Anyhow, so now that's stored correctly. So now I'm going to do 0.05 divided by 7.2. Oops, 7.2. So that fraction, now I take the natural log of it. Again, most calculators, you have to do that back. You hit the natural log first. So now I'm going to divide it by the negative natural log of 2. So divided by, and so I'm just going to hit that recall. So that, of course, that's it. And then, so you multiply this number by 8, right? Because that's the half-life. So times 8. This will give me the number of days that have gone by. All right. So if I rounded it to one place past the decimal, it would be 57.4 days. All right. So let me write that. 57.4 days. All right. And again, in Blackboard, you would just write the number. It would say something like, how much time has gone by with these conditions. It would be 57.4. So that you just put the number in. All right. And then it would ask you, how many days have gone by. All right. So that's how this works. If you're just, this is actually more about this is more akin to what you would actually do. You measure the amount you started with, the amount that remains, and then you want to know how much time has gone by. All right, so this is more of a natural way of using the radioactive decay. All right, so you got to use these natural logarithms, but we're not going to, again, you just plug into this formula and you'll be fine. All right, so